All right, so today we're going to take a look at section P.4, which is polynomials. And we're going to start out with what feels a little bit like an awkward definition, but it's not as bad as it looks. So just write it down if you don't have your notes already printed, but this is actually the definition of a polynomial, right? It's the formula of a polynomial. A sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus, there's all your dots, and then you have a sub 1 x plus a 0. So let me just talk about what all those letters are representing. All those a's are simply saying that they're different numbers, okay? A sub anything is just a number. Positive, negative, fraction, whole number, doesn't matter, they're just numbers. Okay, so all the a's are numbers. All those exponents are integers, okay? And that's not even true. Let me correct that. They're whole numbers more specifically. So whole numbers, remember, are the numbers 0, 1, 2, 3, 4, and so forth. So all my exponents where it says a to the, or x to the n, that means like it's x to the 5th or x to the 100th, okay? So those are the x with powers that are whole numbers. Polynomials are actually named by how many terms they have. So each term is what's separated by each addition. So these are our terms that I'm underlining. And the number of terms give it its name. So if it's one term, we call it a monomial. Right? Mono, one. If it's two terms, it's called a binomial. Two for bi, or bi for two. And if it's three terms, it's called a trinomial. Try for three. And anything bigger than that doesn't have a specific name. We just say polynomial. And in fact, we can say polynomial for the ones that are monomials and so forth too. It's just that we have a more specific name for them as well. Okay. There's one more piece of definition information that we're going to do, but we're going to do it within a problem. So example number 1 is a polynomial. It's negative x to the 7th minus 6x to the 4th. Okay? And it asks us a couple of questions that I haven't actually identified for you what they are yet, though you might remember. It asks for the degree and for the leading coefficient. So degree actually means the largest exponent. So by way of example, what is the degree for this polynomial? So exponents, we're looking at the exponents. 7. It's a 7. So the largest exponent here is the 7. So my degree is 7. And then the leading coefficient is the coefficient. Yeah, somebody's already trying to tell it to me. It's the coefficient or the number in front of the, I'm going to call it degreed term. So that term that I just identified as being the largest degree, that number 7 right here, it's the coefficient in front of it. So somebody said before just a minute ago negative, but it's negative what? It's negative 1. So my leading coefficient, which I can just abbreviate as LC, is 1. Sorry, negative 1. I meant to write the negative there with it. It's negative 1. So it's just the beginning term. If it's the largest term anyway, we usually see them written that way. So as we start to simplify, we're going to do addition, subtraction, multiplication, division with polynomials. A lot of things that we're going to do as we work with them are going to, at least in the end, somewhere along the way, result in finding like terms and combining them. So we've got the 3x squared and we've got a 5x squared here, right? Those are like terms because they both have x squared. That's what makes them alike. So at that point, we can actually just combine them using our traditional methods for addition or subtraction, multiplication, division, whatever we're looking at the moment. So the the negative 3 and then the positive 5 would give me a positive 2. So this would be 2x squared. The next one, which is negative 4x, I also have a negative 8x. Those are alike because they both have just the single x with an exponent of 1 attached to them. So negative 4 and negative 8 are negative 12. So it's negative 12x. And then the last pieces are my constants. I have positive 2 and negative 7, which gives me a negative 5. Okay, so addition, without a doubt, is the cleanest one to do. Subtraction is not much worse. It's just that we have to be a little more careful because there is a negative between them. So if you're good at sort of thinking through this without rewriting, you can just jump to the solution on that, and that's okay. But what I find more often than not is that negative in the middle will mess something up if you don't actually distribute it physically first. You'll actually make a mistake. So I'm going to show what happens by distributing it first. So all my negatives are going to go, that negative is going to go through the entire second term, the second polynomial, excuse me. So negative x squared, negative 4x, and negative 4. Everything at the beginning stays the same. And I don't really need the parentheses at all around them. If I distribute the negative through like that, then it becomes just like the last problem. I'm just combining like terms. So I have x squared and have negative x squared. Those cancel out, right? So those actually add to 0, so I don't actually have any x squareds. I have a positive 2x and a negative 4x. So it's negative 2x. And then I have a positive 4 and a negative 4. Those also happen to cancel out. So this actually ends up in a very simplified example. It's negative 2x. It's a monomial. Okay, so we're moving quick because hopefully this is very old hat. So bear with me as we move through them. But we're doing multiplication next. So one of the things that you might have remembered, there's a couple different things. You might remember the word distribute. That's really what we're doing generally speaking. Specifically, when it's a binomial by a binomial, you might remember the acronym FOIL. And then I want to show you another one just because it's fun. And so we're going to do like this. Okay, I'm just going to draw my arrows a little bit differently because I had a student do this when I was supervising student teaching, and she said, look, it's a smiley face. So it doesn't matter what order you distribute things in. It is completely and utterly irrelevant. But you need to make sure you take every term in the first polynomial times every term in the second polynomial. So if I have my arrows drawn like this, or my curves drawn like this, like I do, I'll start with the first one, 2y. So 2y times 3y is 6y. And remember from polynomial, or from exponents that we did earlier, it's 6y squared. So you guys did that well. If I move through to the next term, right, if I'm following my curves maybe, I've got the negative 1 times 4. So negative 1 times 4 would be negative 4. And then if I move down on bottom, I've got the 2y at the beginning times the 4 at the end. 8y, right? We're multiplying. 2 times 4 is 8. And then I have the one that's the sort of the piece right here in the middle. And I have the negative 1 times the 3y, which is negative 3y. Okay, so that's the multiplication. If you do it in a different order, it's fine. It doesn't matter in the slightest. There's one thing we have to do, and then there's one thing that we have an option of doing. The one thing that we have to do is to combine these two because they are alike, right? They're both y's. They can combine their like terms. So I have the 6y squared, I have the negative 4, and then I have 8y minus 3y, which would be 5y. So it's actually perfectly okay if you leave it like that. There's nothing wrong with it. But some of you are cringing. Inwardly, I'm cringing too. I like structure and order, and so I would never leave it like this because to me that would bother me. So a more standard notation to put it in is what's called decreasing order of exponents. So we do our y squared term, and then we do our y term, and then we do our constant term. But to be honest, if you stopped right there, nobody's taken any points off for homework or anything like that either, okay? So we would write that if we wanted it in that order, 6y squared plus 5y and minus 4. So either of those will be okay. Any questions so far? Awesome. So I would be remiss if I didn't sort of mention one where it's not a binomial times a binomial. So this one has a binomial. Remember, it has 2 terms at the beginning. But the second set of parentheses has 3 terms in it. It's a trinomial. What that does is it means that that whole acronym FOIL, it doesn't work at all. Because you don't have a first, outer, and an inner on the last term. You just don't. You don't have a multiplication of 4 terms when you're done. You actually will have 6 terms when you're done. So the way that I keep track of them, and again, this is just the way that I think about them, is that I take the first term and I distribute it through all of the second set of parentheses. So I have x times 3x squared, which is 3x cubed. X times negative 5x, negative 5x squared. And then x times 2, which is 2x. Okay, so that's the x, the first one. And I'm going to go just underneath it so I don't clutter up all my lines and arrows and things I'm drawing. And I'm going to do the same thing with the negative 3, being real careful to remember that it is, in fact, negative. So I have negative 3 times 3x squared. Yeah, negative 9x squared. Negative 3 times negative 5x. That one's positive, yeah, 15x. And then negative 3 times 2, negative 6. Okay. If you've not missed any terms, you should have 6 of these at this point. Okay, we do have 6. But it's kind of a real quick check step to make sure you didn't miss anything if you count those up. And then we'll combine like terms. And as we do it this time, we'll actually keep them in descending order of exponents. And so I have my 3x cubed. It's the only x cubed. But then there's an x squared here and over here. So how many x squareds do I have? Well, I have 2 terms of them, but how many? Like, what's the coefficient in front going to be? Negative 14, because I have negative 5 and negative 9, so there's negative 14. Then I have x terms, so there's a 2 and x and a 15x. So that's 17x. And then my constant happens to be all by itself back there, so I'll rewrite that. So depending on what you're actually multiplying, if things condense, you aren't going to have 6 terms at the end. But if depending on what you're multiplying, you might actually not be able to combine anything, and there might be 6 terms at the end. That's a possibility, just depending on what the terms are. All right, so you might feel like number 6 sort of shows up in an arbitrary place. We talked about radicals last time. We didn't, this is not a polynomial, okay? So it is not a polynomial. But the reason it's showing up in the polynomial section is because of its similarities and the way it operates to polynomials. So as you're noticing this, we have 2 radical expressions, right? And they're binomials in the sense that they are binomials. They just don't have any x's in them, right? They are 2 terms. Right? So we're still going to be able to do the same things that we've done basically back over here with number 4. First, outer, inner, last, make a smiley face, distribute, whatever, thinking process it is that you like. I'm going to do FOIL on this one since I didn't do it on the last one. And for those of you who maybe that's not a familiar acronym to, you'll see what we mean. So FOIL says I do the first terms first. So 5 times 4. 20. You can start out with that one nice and easy. Then we do the outer terms. So we do the terms on the outer side. So I have 5 and I have negative 3x squared. So here's the way it works when we have radicals. Anything that's on the outside of the radicals gets multiplied. Anything that's underneath the radicals gets multiplied. Now in this particular part of the problem, I only have a 5 in one of the terms, right? I don't have a radical next to the 5. It's just 5. So the 5 will multiply by the 3 because it's also on the outside to give me negative 15, but nothing gets multiplied by the square root of 2 because there isn't a radical next to the 5 that's being multiplied, right, attached to it like multiplied by it. So that's the first in the outer. And then my inner is these 2 pieces. So again, one of them's inside the radical, that's the 2, that's the radicand. The 4 is a whole number, it's not inside a radical. So I have to keep the 4 on the outside, 2 on the inside. So this is actually just 4 square root 2. Okay? And then my last terms. I have a square root of 2 and I have a 3 square root of 2. The 3 is the only thing on the outside, so it will stay on the outside. It's negative. And then I've got square root of 2 and I've got 2 square roots of 2. So this isn't the only way to write it, but basically what happens, because I want to show you what happens if they weren't the same, is that they both stay underneath the radical. Now, the kicker, of course, is that we encountered last time that when this happens, that when we have 2 things underneath the square root, we can pull them out. So this isn't going to stay underneath there for long because it simplifies. But if one of them had been a square root of 2 and the other had been a square root of 3, that wouldn't happen. And we would still just have 2 times 3 underneath the radical. On this one, it simplifies. Okay? You can also think of it on this one such as I have 2 times 2, which is 4. And what's the square root of 4? 2. So you can think of it from that perspective as well. So right now, I've got a 20 here. I can combine these two, negative 15 and positive 4. I can combine them again because they are alike. They've got the same radicand piece. So what is negative 15 and positive 4? Negative 11. And then my last piece is actually now 3 times 2, which is mysteriously quite like 6, right? So that's 6 at the end here. The whole thing's not 6, just that last piece. Can combine with the 20 at the beginning. Oh, it's negative. Sorry, thank you. So it can combine with the 20 at the beginning. The negative 6 can combine with the 20 at the beginning. So with the 20 at the beginning, the negative 6 at the end, which gives me 14. Good catch. I mess negatives a lot, so keep me on my toes, please. So you have 14 minus 11 square root of 2. And why can't I combine those? One of them's a radical and the other one's not, right? Yeah. Okay. Okay, we encountered this idea of rationalizing last time, and I kind of did one of those bad teacher things where I said, I'm teaching you something that I don't really like, right? It's like when your parents admit that they don't really like something they have to do as your parents. That's what I did, right? I was like, I don't really like this, but it's part of what we do, and there is a reason for it, but many of you won't encounter it, so I'm going to show you how to do it, but there's a lot of times when it doesn't really look simpler and stuff like that. Well, we're encountering rationalization here again. What you'll notice in this denominator, though, is it's not a single radical this time, right? When we had it in the last section, it was just square root 2 in the denominator or square root 5 in the denominator. And the way we eliminated that square root is we multiplied the numerator and the denominator by that square root. Shake your head if you know I'm remembering this from repeated. Good. Okay. The primary difference in what we're doing here is not that there's 2 things in the denominator, but that there's 2 terms. Namely, that they're separated with addition or subtraction. So if I were to try, for example, on this, to multiply by square root 8, it wouldn't help. Because multiplying by the square root of 8 to the square root of 8 would get rid of it here, but now the note would be attached to the 3. Right? So it doesn't help me to just multiply by square root of 8. Likewise, if I multiply by the denominator as it is, namely 3 plus square root of 8, I will still end up with some square root of 8s. So what we're going to do is something called multiplying by the conjugate. So the conjugate of a term, or of a binomial, is the same terms, but with a different sign in the middle. So instead of 3 plus square root of 8, we do 3 minus the square root of 8. Okay? So trust me for a moment, but I'm going to start with the denominator because I want to show you that it really does work itself out. So I've got a binomial times a binomial in the denominator, right? So I can FOIL. So if I do my first terms, that's going to give me 9. If I do my outer terms, I've got negative 3 square root 8. And notice what happens when I do my inner term. They cancel, right? The outer and the inner terms cancel. And one of the things that might be in the back of your mind, like I kind of feel like I've seen this before, but I don't remember, and it wasn't quite like this. So this is actually a difference of squares. Okay, so we encounter it when we multiply any time by conjugates, whether there's radicals involved or not. This happens. My last terms then, right, the square root of 8 times the square root of 8, one of them is negative, but give me the 8. So in fact, I eliminate radicals every time I do this in my denominator, which was the goal, by the way. So that's good. We achieved that goal. This is actually really nice even because notice my denominator is now 9 minus 8. It's a wonderful denominator, isn't it? You betcha, it's 1. So my denominator became 1. That's definitely not going to always happen. That just was lucky, okay? Now, I still have to do the multiplication of the numerator, and I'm still going to get some radicals usually on top when I do that. I don't have things cancel out beautifully in the numerator, just the denominator will. So let's go back up now to the numerator. So I'm going to take the square root of 2 and distribute it through. So square root of 2 times 3 is 3 square roots of 2. Square root of 2 times square root of 8. So on this one, the 2 and the 8 come underneath the radical together, but what's 2 times 8? 16. So on this one, it actually does simplify nicely. That's friendly. It doesn't always happen, but that one's pretty friendly. We'll do our other piece. So we've got the 5. So 5 times 3 is 15. And then 5 times the negative square root of 8 would be, well, negative 5 square roots of 8. Okay? Good so far. Okay, so we already said this wonderful thing happened in our denominator. Just this particular time there's a 1. I'm going to write it just for now so that you, if you're looking back later, you're like, where'd the numbers go? You don't have to actually calculate it again, but it's a 1. The 3 square root of 2 at the beginning can stay put. The negative square root of 16 would actually be negative 4. But I do need to do a little simplification right here because 8 is not prime like 2 was. 8 can break down. It's 2 square root of 2. And if you're wondering where that comes from, remember you can break it down like this. And you see 2 2's that you can pull a 2 out. So the square root of 8 is actually the same as 2 square roots of 2. That 2 will get multiplied by the 5. So I actually have 10. Was it positive? Yeah, I think. I've got so much going on my screen. It's negative. Okay, thank you. So, what's that? Oh, there's a 15 I missed. Thank you. So I have a positive 15, and then I have my negative, and then it'll be 10. Okay, did I catch them all now? Okay, thank you. I was getting so excited about that square root of 8. We've got to talk about that I forgot the 15. All right, and then there's still a square root of 2 there. Okay, so I have a little bit to clean up on top. The denominator, I'm not going to write it again, actually. We'll just leave it off because it's obviously, at this point, irrelevant. But I have a 3 square root of 10, a 2, and a negative 10 square root of 2, which gives me negative 7 square root of 2. You can write it at the beginning or write it at the end. It doesn't matter. And then negative 4 and positive 15 is 11. So either write it this way or you can write it as 11 minus 7 square root of 2. So let me give you sort of a thought about these. Obviously, if you're dealing with a problem that's odd, you can check the back of the book, make sure you got the exact answer, and that's wonderful. I mean, there's going to be work you're going to show. Like, there's no way you're going to get from the beginning of this to the end of this without some work, okay? But if this is an even problem and you're just wanting to know, did I get the right answer, right? Something that you could do with your calculator to confirm is that you could put this original, the one that's in the black type, that expression into your calculator. Just make sure the entire numerator is in parentheses, the entire denominator is in parentheses, and press enter. It'll give you a horrendously ugly decimal, okay? But then you could put the same value that you got as your answer in there. And if you did it right, it should give you the same horrendously ugly decimal. And you could confirm that, in fact, you made no mistakes by doing it that way. Or maybe you did make a mistake, and now you can go back and look for it. Okay? So utilizing a calculator in an effective way, that would be one of them on this particular problem. Any questions on that one? Okay.